Welcome everyone. In this video, I want to go over the fundamental theorem of calculus. And we're going to talk about the definition first and why in the proof, of course. So, and in other recordings, I have some examples of that. But let's go over the definition first. It says if f is defined on the interval AB and x varies between a and b, then we can write the following. So you can say g of x, the function g of x can be written as the integral going from a to x of f of d dt. In this case, a is a constant, just a number. And if f is a positive function, then g of x can be interpreted as the area under the graph of f from a to x. Let's look at it. So if this is the function of f of x, when we take the integral of a function, what we get is the area under the curve. So basically, this limit, the upper limit in this case, is not a constant. It's a variable and it varies. So as x changes, this area changes, and this is just g of x. So the function g of x can be written as this integral. Now, I put a note here for you. G of x is defined as the antiderivative of f. That means f of x is the derivative of g of x, or g prime of x equals to f of x. Let's look at a simple example, see how this works. If I write the same definition for this simple function, t squared, I can say g of x equals to the integral, again, going from a to x of t squared dt. Now, usually we don't evaluate those, but we're going to go ahead and evaluate this and see what happens. So now if I say find g prime of x is just g of x is in the antiderivative of f of t, so g prime of x is just going to be that function. So very fast. No, we don't need to evaluate this integral to find the derivative. You just put x squared. But let's check, see what's going on. If I evaluate this integral t squared dt, the integral of t squared is t cubed over 3. And again, we're going to go from a to x. So we substitute x first and minus a. Then we get x cubed over 3 minus a cubed over 3. So basically, this is our function, g of x. It here too. So it's g of x is x cubed over 3 minus a cubed over 3. Let's take the derivative of that. G prime of x is 3x squared over 3 minus, this is a constant. The derivative of a constant is 0. So we just end up with x squared. Here we got that without even taking the integral, and you should not take the integral here. So if you're asked to find the derivative of g of x, you just put that function. And that's when the upper limit here is x. If it's another function that then changes and we use the chain rule, but that's not what we're gonna concentrate on this video. So now I put the note also for you to find g prime of x. You don't need to integrate g of x equal to, or you don't need to integrate this part. So g prime of x is simply f of x. So you just copy that function and you're done. And again, that's in the case if the variable is x and it's not a function, this upper limit, it has to be x. If it's another function, as I said, we have to use the chain rule, but that's we will go over that when we do more examples. Now we want to see the proof of that. So the proof, well, let's go over the definition one more time and I'll talk about the proof. So we said if f is continuous on the closed interval AB, then the function g is defined by that. So g of x equals to the integral of f of the dt going from a to x, and x is a number between a and b, and again b is another number. So we start from a and we can go to b. If b is defined, then it's just going to be a number. It could be just going to be an integral, a number, but in this case, this varies. Now, the function g of x is continuous on the interval ab and differentiable on the open interval ab, and we can say g prime of x equals to f of x. So this is the fundamental theorem of calculus. That's what we want to prove. So what's the goal of our proof? We need to show by the limit definition of the derivative, which is, we know that the derivative of g of x, g prime of x is limit as h approaches to 0 of g of x plus h minus g of x over h. So we need to show that that is going to be equal to f of x. So let's proceed. Now, first of all, we know that x and x plus h, these are numbers between a and b. So if I write g of x plus h minus g of x, we go to this definition again. And for g of x plus h, for x, we substitute x plus h. And that's what I did here. So g of x plus h is going to be a to x plus h. Again, that's the integral of f of t dt minus a to x, and that's g of x of the integral of f of t dt. Now, just this part, we can use one of the properties of the integral. We learned that when we go from a to c, that's why I just wrote the property here. The integral of f of x ds from a to c can be written as, we can go from a to b, separate that, and b to c. And that's what we do here. So the integral going from a to x plus h, we can take this integral going from a to x and x to x plus h. These are the same number, just like here. So make sure to go over that property again, and you'll see how that makes sense. Minus, we bring this down, the same thing, it comes down. Why did we do that? Because it makes it much simpler. Now we know we can cancel these two, and we're just left with that. And this is g of x plus h minus g of x. So, and for h not equal to 0, and I wrote it here, g of x plus h minus g of x over h is just this quantity over h, or you can write 1 over h times the integral. So now once we have this, the next goal, so we have this expression. Now we want to know what happens as the limit as h approaches to 0. Let's look at this graph. So understand the limits better. The first thing, so h is right here. So if you're going from x to x plus h, so that's the distance. So there is, by the extreme value theorem, so when f is continuous, when we go from a point to another point, so then we're going to have, and when x varies, we're going to have in that interval an absolute mean, which I called little m, and an absolute max, which I called big M. So little m is our mean, and big M, that's how we're going to call it, is our max. So absolute mean and absolute max. The other thing that I want you to notice in this case, as h approaches to 0, then for m, I called it u, and for the x value, I called it u, and for big M, the x value, I called it v. As h approaches to 0, you know u is going to approach to x. And as h approaches to 0, v also will approach to x. Why we did that? So first we can write m as f of u. So this is our m, and that's f of u. And big M as f of v. So that's our m, which is of v. So they're both on this interval. So now there's a property says, why do we consider the mean and the max? So we know from the property of estimating the integrals, if our function is between m, little m, and big M, then the integral is going to be between m times b minus a and big M times b minus a. So this is one of the properties that we have seen in the previous lectures. So that's why we use this to estimate integrals, and we're going to use that here. So I can put our integral between m times x plus h minus x, because our limits are x plus h and x, and big M times x plus h minus x. So basically x is cancelled. So you have little m times h and big M times h on this side. Now if we divide everything by h, which I'll do that very soon. So, but let's substitute little m. We know that that's f of u, and big M, we call that f of v. So if we divide all three sides by h, then that's what we get. F of u, 1 over h times the integral, and that's less than f of v. So, but what is that? We know that was just the expression g of x plus h minus g of x over h, and we saw that in the beginning of the proof. So if I scroll down, so we have that. So all I did, I substituted that by this expression. So right here. Now, since u and v lie between x and x plus h, I went over these two. When the limit as h approaches to 0 of f of u, as h approaches to 0, u is going to approach to x. So f of u becomes f of x. As h approaches to 0, v is going to approach to x also. So f of v is can be written as f of x. So both of those limits as h approaches to 0, that becomes f of x, and that becomes f of x. So, and by the squeeze theorem of limits, we learned that if limit as h approaches to 0 of f of u equals to f of x, and the limit as h approaches to 0 of f of v is f of x, then the limit as h approaches to 0 of g of x plus h minus g of x over h is also f of x. So, and this was the definition of the derivative for g prime of x, and that's g prime of x, and that equals to f of x. So, and I said therefore f of x equals to g prime of x. So that's the proof. Thank you for watching, and I will see you in the next recordings. Have a good one, everyone.